Hello everyone, welcome back to this course again on discrete mathematics, and today we are going to deal with the third part of this section on relations. And today we are going to examine various practical aspects of this section on relations. We have already seen different properties of relations. Let's see how to represent relations using directed graphs. A directed graph consists of, say, you have a set of V of vertices or nodes, then you have edges or these elements that connects one node with another one. It's like just like a line that connects the node. If A comma B is in the relation, then there is an arrow from A to B. So we generally use the relation on single set, considering our relations A comma B such that A divides B. Say for example, what we do is usually the old way is that A is related to B. Here 1 divides 1, 1 divides 2, 1 divides 3 and 1 divides 4. We know that they are connected, and this is how we used to do in the past. And again 2 divides 2, 2 divides 4, 3 divides 3, 4 divides 4. That's how we used to do. And this is further expressed in this form of matrix, as you can see here, where 1 divides itself and then it can divide 4. So 4 it's connected to 4, it can divide 3, connected to 3, it can divide 2, so it connected to 2. Then 2 divides itself, so there is a loop there. Then 2 can divide 4, so it connected to 4. 4 divides itself, so it's a loop there. 3 divides itself. So this is another way of expressing using a directed graph. And this 1, 2, 3, 4 can represent the nodes or vertices, and these arrows are the edges. Let's see how we can express a reflexive relation using graphs. Less than or equal to the one which every element is related to itself. If you recall the definition of reflexive, let's say A, the set A have 1, 2, 3, 4, 5. So if every node has a loop, a relation is reflexive when you have the loop, because they are related to itself. So in this graph you can see the node 1, 2, 3, 4, 5, they have a loop in it. So A is related to itself, that is 1 is related to itself, 2 is related to itself, 3 is related to itself, 4 is related to itself, and so on. Irreflexive, less than the one which every element is not related to itself. So when the elements are not related to itself, we can say it is irreflexive. So you have again, if every node does not have a loop, a relation is irreflexive. So you can see here again 1, 2, 3, 4, 5, the nodes, they don't have a loop. In other words, they are not referring to itself. 1 is not referring to itself, 2, 3, 4 and 5. So this is the irreflexive property. Coming back to the symmetry section. So as you can see, symmetric relation, one which if A is related to B and B is related to A for all A comma B, which means that you have the relation, say if 1 is related to 3, then 3 has to be related to 1. If 1 is related to 4, then the 4 has to be related to 1. If 1 is related to 5, then 5 has to be related back to 1. So in other words, if there is an arrow from 1 to 3, then there should be an arrow from 3 to 1. That is the symmetric property. So if for every edge there is an edge in other direction, then the relation is symmetric. Yeah, that's it. Whenever you have an edge or the arrow that goes from one node to another node, then you should have an arrow coming back again to the same node. That reflects the property of symmetric. So loops are not allowed and do not need edge in other direction. Yeah, the loops are not allowed in this part. Note that this relation is neither reflexive nor irreflexive. Right. Let's see here, this one is called anti-parallel pairs. So they are kind of anti-parallel because when you have an edge from 1 to 3 and you have a parallel edge going back to 3 to 1, so they are anti-parallel. Asymmetric, so less than one which if A is related to B, then B is not related to A for all A comma B. So it's quite straightforward because symmetric and asymmetrics are just the opposite. A digraph is asymmetric if, first point is if for every edge there is not an edge on other direction. Yeah, if there is an edge from 1 to 3, there is not an edge from 3 to 1, then the relation is asymmetric. And the loops are not allowed in an asymmetric digraph. We can see here, simple, and this looks like a reflexive property, if you can recall. Well, then let's consider more on this anti-symmetric properties, less than or equal to. Here again, this one which if A is related to B, then B is not related to A unless A equals B for all A comma B. So with this in mind, let's see this section how we can express in terms of graph. For every edge there is not an edge in other direction, then the relation is antisymmetric and loops are allowed in the digraph. So here is how it can be represented. So then it's, at times you can say this is the one that looks like a reflexive property again. Transitivity, less than or equal to the one which if A is related to B and B is related to C, then A is related to C for all A comma B, B comma C and C comma A. So again, a digraph is transitive if for there is an edge from A to C and there is an edge from A to B, then there should be an edge from B to C. So you can see here, if you see closely, you might examine this. So there is an edge from 1 to 2, then there is an edge from 2 to 3, and there is an edge from 1 to 3. It's like 1 is related to 2 and 2 is related to 3. Again, 1 is related to 3. In other words, 1 equals 2, 2 equals 3, then 1 equals 3. It's like A equal to B and B equal to C, then A is equal to C. So the applications of digraph, let's talk about this MapQuest. So this is the map, and you can see it's like a small town with lots of houses, buildings, industries, in fact some trees. Then you have these roads coming out. Let's try to examine further on this map as you try to remove the unwanted things. So we have removed all the buildings, trees and all those stuff. Now what you have is just the directions as well as some very important parts like the street names and all the roads there. Okay, let's remove more information. As you remove more information from this, you just have these junctions, like all those junctions or intersection, you are mapping it to a node or vertex. So now you can see if you try to traverse through this graph, you can see there are a lot of different properties that you can express if you want to move from one point to another point. So now I have removed the map again. So this particular graph that you see here right now, it's just the graph of that small town we talked about. Only thing is we have removed all the unwanted things, so we can examine further on how we can do it. So this is how mapping of things from a real world into a mathematical model is done by means of graph. Let's see more on this information. So we have a loop at every junction, and also we have almost all junctions are connected by various edges. Let's examine further and see how these properties can further be developed. So let's say this is the starting point at the bottom, and in the middle you have this end point. So from the start to finish end, let's say where there are a lot of different directions you can take from one point to another point. And let's talk about the relations from one point to another point, the start point to the end point. So as you can see here, this particular flow of direction in which you are moving from the start to the finish, is it reflexive? No, it's not reflexive. Is it irreflexive? Yes, it is irreflexive. It is not symmetric, though at first initially the two nodes, the 2 points looks like symmetric because this section might look like symmetric, but the whole thing does not look symmetric. It's not asymmetric, it's not antisymmetric, it's not transitive either. Now let's see again, and examine any other properties that would come up with. Okay, let's see if we take this direction, this route to start to finish. Here it is. It's not reflexive. It is irreflexive. It's not reflexive because there is no loop, you could say, and it is irreflexive because there is no loop. It's symmetric. You can see whenever A is equal to B, then B is equal to A. So that is symmetric. It is not an asymmetric, it is not antisymmetric or not transitive. So likewise you can see further, and on looking at a map you can see what kind of property it establishes. So we have sample questions here, and for you to look at these graphs. So I just want to ask you these questions, like which of these graphs give us the reflexive, irreflexive, asymmetric, antisymmetric or transitive property? What do you think? Why don't you try to solve it out? So just for your reference I am giving this results here, but take your time and see whether you are getting similar results. So how many symmetric relations are there on a set with n elements? So that's quite an interesting questions, right? So let's consider the matrix representing symmetric relation R on a set with n elements. So here question is how many symmetric relations you can have. So you have this graph, because we are talking about a general case, it's a very generic informations. The center diagonals can have any values, and the upper diagonals, the so-called upper diagonal triangle, upper triangle is determined, and the lower triangle must be transpose version of the upper one. So that's one of the goals of a symmetric property. And how many ways are there to fill the center diagonal and upper triangle? Well, center diagonal can be of any value. The upper triangle and the lower triangle must represent the transpose version. They should have that relation. So there are n square elements in the matrix and n elements in the center diagonal. Exactly. Then thus you have 2 power n ways to fill zeros and ones in the diagonal alone, and thus you have n square minus n by 2 elements in each triangle, the upper triangle and the lower triangle, which means that you have 2 power n square minus n by 2 ways to fill zeros and ones in the triangle. So you have a property in which it gives you the relation of 2 power 2 square, 2 power n square plus n by 2 possible symmetric relations that can be developed with n elements. So well, we haven't proved much on this particular things. That's been well established statement. I am giving this for your reference, for you to get the idea of symmetric relations with regards to n elements and in terms of matrix relation. Relational closures. So this is one of the types that we see. The three types we will study are reflexive, transitive and symmetric. These are the three relational properties in which we are going to talk about the relational closures. So reflexive as well as symmetric relational closures are quite easy for us, whereas when it comes to transitive it's a little bit hard to understand. But anyway, we are going to see all these three elements. So considering the relation of relation R, so we are taking this map that we have seen earlier. So for the MapQuest examples that we had here, note that it is not reflexive. So we want to add edges to make the relation reflexive. So what we are going to do if you want to make it as reflexive? Can you recall how do you make a graph into reflexive? Yes, just add the edges, add the loop. All the nodes should have a loop. That's one of the main requirement of a reflexive property. So that's the reflexive closure. By adding those edges, we have made a non-reflexive relation R into a reflexive relation. Well, then this new relation is a reflexive closure of R. Now the question is, in order to find a reflexive closure of a relation R, we add a loop to each node that does not have a loop. So does this reflexive closure R is R union this delta, where delta is a comma a such that a is an element of R. Let's see, call the diagonal relation. Say with matrix we get diagonal to all. Let's say here let R be a relation on set 0, 1, 2, 3 containing the ordered pair 0, 1, 1, 1, 1, 2, 2, 0, 2, 2 and 3, 0. So with this you can see here 1, 1 and 2, 2 is there. So you have a loop there in this set, and 0, 1 is connected and 2, 0 is connected, 3, 0 is also connected. So what is the reflexive closure of R now? So what is missing? As you can see here, there are two nodes does not have a loop. So we have to add all pairs of edges a comma a that do not already exist. That's right. At node 0 and node 3 there is no loop, so we are adding these edges to make it as a reflexive closure. That's it. We add 0, 0 and 3, 3 to the given ordered pair, by which we make this as a reflexive closure. Now is that we have done with the reflexive closure, let's talk about the symmetric closures. We know that reflexive and symmetrics are quite easy, so let's quickly see what a symmetric closure is. So we have taken the same example of this MapQuest, and we know that this given graph is not asymmetric. If you want to make it as a symmetric, what you have to do? We have to add edges to make the relation symmetric. So recall the symmetric relations. So whenever you have a relation from A to B, then there should be a relation from B to A. So that's the symmetric. So but some parts of this has, like for example, this node, and this node, they have symmetric property, but from here to here they are not having a symmetric properties because nothing is going back The same is true with other elements over here. So let's add the edges so that each and every node has something coming back like both directions. By adding those edges, we have made this non-symmetric relation R into a symmetric relations, or in other words, we come up with this symmetric closure. Yes, so in order to find a symmetric closure of a relation R, we add an edge from A to B, where there is already an edge from B to A. So we have the edge from both directions. So then you have this symmetric closure of R is R union R. This one here you have this of this form R inverse. So if R is A comma B such that, then R inverse is B comma A such that. So let's say R be a relation on set 0, 1, 2, 3 containing the ordered pair 0, 1, 1, 1, 1, 2, 2, 0, 2, 2 and 3, 0. Then you have this given graph. So what are we to do to make it as symmetric? You can see there is things to be added. Yes, we add all pairs of edges A comma B where B comma A exist. So can you see that? We make all single edges into an anti-parallel edges. That's it. You already have 0, 1, but 1, 0 is not there, so you are adding that. Again, you already have 3, 0, but 0, 3 is not there, so you are adding that. Likewise, 1, 2 is already there, but 2, 1 is not there, you are adding. Again, 2, 0 is there, but 0, 2 is not there. You are adding all those stuff. Yeah, 0, 2, 0, 3, 1, 0, 2, 1 is added in order to make this as symmetric closure. Paths in directed graph. A path is a sequence of connected edges from vertex A to vertex B. Here it is. So you can think of the path, for example, starting from A to the end B. You can think of the path that you take from node as certain directions. So that is a sequence of connected edges. You have a sequence of connected edges in this example there. It can be of many different directions that we talk about. So in this example, you can see we have different ways to reach the edge. If the starting is at that part at the top, no path exists from noted starter location because you cannot come back. There is no arrows that is coming back to any other place. A path that starts and ends at the same vertex is called a circuit or cycle. Yeah, sometimes you are in kind of a cycle coming back to each other. Say for example, in this part, start at A and end at B, but you can see it is going in cycle and must have a length greater than or equal to 1. Let's see more on path. The length of path is the number of edges in the path, not the number of nodes. So this is one of the important aspects, as the length of the path is the number of edges in the path, not the number of nodes. For example, if you note this path where you have the cycle, you can see there are 1, 2, 3, 4. There are 4 edges, 4 arrows that take back to the same location where it has started. So likewise, when you have a path, the length of the path is the number of edges in the path, not the number of nodes. At times people get confused saying that node give us more information of a path, but it's in fact is the edges. And in fact we also know that edges has to pass through the node. So at times people get confused with the nodes in other sets. Okay, shortest path. Often these properties that we have here can help us to realize the different problems that we have. So what we have really is that to find the shortest path between two vertices, because you already have a different directions in which you can reach the destination, but what is the shortest path? For example, if you are talking about going from one location to another location in a city, or even in a country, if you want to go from one place to another place, you have to pass through different lanes, different roads. If you are talking about a bigger area in a country where you want to go from one place to another, maybe you have to pass from different cities, in fact. So how is this possible from going from one place to another place? For example, the so-called the traveling salesman problem is one problem where he has to pass through different places. For example, if you are talking about a person that goes, say he starts from Washington and goes on to different locations, different cities, say St. Paul or Salem or San Jose, Little Rock, and back to Washington. So what is the best way to travel? Yes, transitive closure can give us some hint on that. Say for example, this JFK in New York City there, and Long Beach. So if these are the two nodes there, and then in between you have Las Vegas. There's one here again. There is one over in the Florida. So Las Vegas to this point, Fort Lauderdale, and San Diego there. So as you can see, the transitive closure would contain the edge between all nodes reachable by a path of any length. So you can think of this transitive closure like going from say Long Beach to San Diego, San Diego to Las Vegas, Las Vegas to Fort Lauderdale. So these are different way to reach by means of this transitive relation. As you see, the edge between all nodes can be reached by this path. Anyway, we'll examine further the informal definition. As we can see, if there is a path from A to B, then there should be an edge from A to B, generally speaking of transitive closure. Let's take this definition. In order to find the transitive closure of a relation R, we add an edge from A to C when there is an edge from A to B and B to C. So that's like talking about this part. We already have an edge from Long Beach to San Diego and San Diego to Las Vegas. If you want to establish a transitive closure, you can add an edge to provide this transitive property. Say R is 1, 2, 2, 3, and 3, 4. So you have 1 is related to 2, 2 is related to 3, 3 is related to 4. You can think of this transitive like the properties, 1, 3. If you add 1, 3, then you have this property of transitive between this 1, 2, and 3 nodes, because 1 is already related to 2 and 2 is already related to 3. Therefore, you want to connect 1 and 3 to make it as transitive. Again, the other way is like 2 is already connected to 3 and 3 is already connected to 4. Then if you have 2 and 4 connected, then again you have a transitive property. Yes. And again, you can think of other 1 and 4 with no edges there. So again, with the informal definition, we have this, in order to find the transitive closure of R, we add an edge from A to C when there is an edge from B to A to B and B to C. We can repeat this until you get all these relations done. So we are adding this part like even 1 and 4. So this has been repeated again. So this is seems to be quite interesting part, because the transitive closures in real time, they can have a great significance in solving the real time problems. At last, as we talk about the shortest path, as we talk about the connections and relations, there is something called 6th degree of separations. The idea that everybody in the world is connected by 6th degree of separation. It's like the problem that has been developed a long time ago, more than 50 years, in fact 70 years before, people already talked about this kind of relations. Like they at times even the researchers, they did the actual practical examples with the 6 degree of separation, they in fact try to contact people using letter writing, because before 70 years we didn't have internet, but now this, in fact the 6 degree of separation is reducing because of the social media and other things in which people are connected by various means. Yes, 1 degree of separation means you know or have met somebody else. Let R be the relation on a set of all people in the world, and A comma B is an element of R if person A has met person B. So 6 degree of separation for any two people A and G means, for example, here you talk about a person A has met person B. For example, like you know someone by means of some friends or other things, then that person might know another person through some relations, and that another person might know another person. So right now we are talking about like 3 degree of separation. Likewise, a person, anyone or everybody in this world is connected by means of 6 degree of separation at most. A random person somewhere in Mongolia may know a person in another person in the Mongolia, and that guy might know another person maybe in China, for example, and then that guy may know another person in, say, China, then that guy know another person in Korea, and that guy know another person in, say, Australia, that guy may know another person in another part of Asia, then this guy knows you. So that's kind of how this thought of 6 degree of separation established. We are talking about relations actually. So this recent times, this kind of research is being quite hot because of social IoT as well as the so-called a small world problem. The world is becoming small. In fact, the small world problem is talks about the connections between people. Well, I don't want to go deep on that, as we are still talking about the relations. I like to examine further on this thought that we are having here. So at this time we are talking about this relation in general. Like as I told you here, people are separated by means of 6 degree or 6 connections, 6 levels. So if A is connected to B and B is connected to C, C is connected to D, D is connected to E, E is connected to F, and F is connected to G. That's it. The whole world is kind of connected. It's kind of R power 6 degree of separations. So we are not going to examine further on this particular research topic that is open for everyone. Like as I told you, social IoT and small world problems are hot topics of today's relational development. And as we move on with this topic of relations, I would like to share more on this relation issue in the coming lectures as well. So until I see you in the next lecture, have a good time and goodbye.